Hi, this is now our full second full beam design example. This one will be real because we're going to look at a true wood cross section, and note that what we're going to have here is a series of dimensional pieces of lumber that are 2 by 6. Right now, a real 2-inch by 6-inch dimensional lumber in the U.S. is not 2 inches by 6 inches. It is instead 5.5 by 1.5. The rough cut of it would be about 2 inches by 6 inches, and then they would dress it or trim it down so that it would be down dimensionally here at the 5.5 and 1.5. Right, and so we're going to stack them up, and in a typical glue-laminated timber situation, then you'd have epoxy type glue that would bond those two layers together. When we get into the next module, the shear stresses that are induced during bending, we'll get the opportunity to look at, well, what's the strength of that that glue, that epoxy need to be, right? So we'll worry about that part later. First, we're just going to size this overall cross section so that it is sufficient for the flexural stress or the normal stress that is induced during bending. Right? So we know what the width of this thing is. We don't know its height, and we don't know how many of these 2 by 6s we need to get the desired height. And that's a part of what we're all after, right? This particular species of wood has an allowable stress in bending of 3 KSI that's given to us in the problem statement. And our physical setup is that we have a beam that is spanning across a gap that is 20 feet long, and it in its service or design level load that we're looking at here as supporting 1,000 pounds or 1 kip per foot along the beam. Of course, 1 kip per foot times 20 feet means that we have 20 kips or 20,000 pounds of loading spread out over the length of this beam. Now, one other critical part here about the design that we're doing here is that this is purely the normal stress during bending, right? So that's, of course, coming along and thinking about our sponge beam, and we're bending it, in this case, in a smiley face kind of fashion, right? Compression on the top fiber. And this is going to be a very tall beam compared to its width, which means that we have to worry about the beam when it gets loaded up, that compression flange becoming unstable. And that phenomenon called lateral torsional buckling is something that you would learn about in another class. So if we were to properly support that compression flange, then we will get the full strength that we're looking at here with this allowable stress of 3 KSI. An important provision there. Just think about a 2 by 4. If you put a 2 by 4 up on its height, so it's tall, and you try to walk across it, it's going to be prone to wanting to flop out of plane. You turn it on its side, all of a sudden it's a lot more stable, but it's also a lot weaker and a lot more flexible. You got a yin and yang thing that you're going with here. So again, important criteria to just keep in mind. We are doing something real, but it's not everything that we have to look at in the design. Right. So we've already been given what the allowable stress is. That means the factor of safety is included. So what we need to find out are the demand from the loading side, and then turn that into a geometric criteria that will then allow us to figure out what height we have to have, and then go select appropriately. All right. So our first thing here is, let's find our maximum moment or demand. And if you've done this one enough times, you know what the answer is. It's WL squared over 8. Where the heck did that come from? Remember here, do a free body diagram on something like this. We've got the applied load of the uniformly distributed load. We've got these 2 vertical reactions at the end. And for the simple case that we have here, that total load gets split evenly between the 2 sides, right? So there's your loading diagram, and then you'd have your shear diagram. Then that would, of course, follow the reaction WL over 2 up, and then we have a uniform load acting downward at constant, so we have constant slope on the shear diagram. We've got then, to find out what it is over here at the far side, we 1 up WL over 2. That change in the shear is given to us by the area of the load diagram, W times L. So WL over 2 minus WL would be, of course, minus WL over 2. And then we go up by the point load that is the reaction that closes off to 0. we have a complete and correct shear diagram. The moment diagram then is going to integrate what the shear diagram is. So shear diagram is a linear function, and so we would end up with a parabola. Same kind of thing in terms of how we work with these things. The moment diagram slope is given to us by the shear, so it's big, and it's exactly equal to WL/2 at the left side for the slope. It's going to be 0 here in the midpoint, so that means that's where the maximum is at. Ooh, that's what we want, isn't it? And it'll turn out to be second order concave down. We're going to go up to the midpoint, right, by this area under the shear diagram. We're integrating the shear to get to the moment, right? So that's 1/2 of the base of L/2 times the height of the WL/2. So 1/2 of WL/2 times L/2 will give us the WL²/8 that I mentioned before. Yeah, I've done this so many times, I know this answer. And of course, on the other side, we'll decrease that same amount of area. That'll take us back to 0, and thus demonstrating that we really do have the maximum positive for this particular situation. So let's do that calculation here. We've got M max equals WL²/8, and our W is then 1 kip per foot times our span length of 20 feet. That whole thing, including the units, is squared, and then divide by 8. Right? Well, 20 feet, the quantity squared is going to be 400 square feet. So 1 kip per foot times 400 square feet will be 400 kip foot. A 400 divided by 8 is going to be 50. So our answer here is that our moment demand is 50 kip foot. Right now, remember, we're probably going to want that in terms of kip inches. So we could convert that right off the bat, 12 inches per foot. And so we will get then for our true demand for a moment of 50 times 12 is 600 kip inches of lateral strength that we need. Right, so that now let's go and find our required geometric property that we need. That's the elastic section modulus. That's required. That's, of course, remember, equal to I/C. That'll be interesting here. I for a beam is going to be 1/12 of the base times the height cubed. C, the distance from the centroid to the outer fiber, is going to be half of the height, right? H/2. So that would be then, BH² / 12/2 is the 6. H cubed over H is then just the H squared. So that's your S from that standpoint, and how we'll connect it over to the shape that we've got over here. And so now we can kind of string this all together, right? S required is equal to our moment demand, so our max moment, divided by our allowable stress. In this case, that would be our 600 kip inches, and then divide by our allowable stress of 3 KSI, gives per square inch. So 600 divided by 3, this is kind of nice, right? A nice little pure academic problem. All the numbers are real nice. That will end pretty fast here, but 600 divided by 3 is just the 200, and the kips go out, divide through, and you have inches over, 1/, inches squared, so that's inches cubed. So you'd have a demand or a requirement here to have 200, at least 200 cubic inches for the S, right? And because now we know how S ties to the geometry, and we know what our width of the cross section is, we can then go find our height that's required, right? So BH² over 6 be set equal to 200 cubic inches, and then transform this. H² then is going to be equal to our 1200 cubic inches divided by our B, which is 5.5 inches. Looks like we have run out of cute numbers that work out really nicely. The inches cubed divided by inch will turn out to be then just square inches. Get your calculator out. 1200, let's see, 1200 divided by 5 is on the order of 20 something or other. And 1200 divided by 5.5, well, 1200 divided by 6 would be 200, right? So 1200 divided by 5.5 is going to be a little bit bigger, and sure enough, it is, right? 218.18 here for that need for the h squared. And we go take, of course, the square root of that, and we find out that h required, that is, that's what we're really working out, is square root of that, which is 14.77 inches high. Right now, each one of these 2x6s is 1.5 inches high, right? So that means that we're not going to have a perfect number of these guys, but let's just find out then. Find the number of 2x6s, and so we'll have then n equal to our h required divided by the h for one of these, and so that'd be 14.77 inches divided by 1.5 inches. So that's like multiplying by 2/3, and so that would be what, a little less than 5. I don't know what math I'm doing, but that was just crazy math. Right, 14.77 divided by 1.5 is about 9.84 or so, right? So of course you're not going to go shave down your 2x6s. That would be silly. What you're going to do is you're going to say, okay, we'll use 10 2x6s. Right? That's pretty high. Compared to its width, it would start to make me a little uncomfortable here, but I don't know where the heck I got 5 out of that. But anyways, we need about 10 of those stacked up and all glued together and bonded together. You can't just stack them up, they do have to be bonded together to make this all work. So there you go, there's your, actually your third one, because in the first one we did, we had 2 parts, a channel as well as a Y flange shape. So this is your third one, right?